Hello, I'm going to talk about waves for any Year 11 that are about to do Paper 2 or an equivalent if you're from another school. So first of all, there are two types of waves that you need to know about. You need to be able to name them, you need to understand the difference between them, and they are transverse and longitudinal. So first of all, an oscillation is essentially a movement back and forth about a central point. So if you imagine a pendulum, so essentially a weight on the end of a string, and you hold the end of it and then the other end you let go, it's going to move back and forth like a grandfather clock about a central point, and you would say that it's oscillating. So for transverse waves, it's not perfect. If you imagine this was a skipping rope and you were holding this end here, and I was holding the other end here, if you wanted to make that shape, you would move the skipping rope up and down. So your oscillation is going to be up and down, but the wave itself will travel from between left and right in this case here, like this. So if you see, the oscillation is perpendicular to the direction of wave travel. Okay, so like this. That's what we've done above. So that's perpendicular to, or at 90 degrees to each other. Okay, so any transverse wave, that will be the case. Whereas for longitudinal, if I draw, let's say, a sound type of wave, this isn't perfect. What will happen is the oscillations will be parallel to or in the same direction as the direction of travel. So if this was a slinky, can you imagine these lines that I've drawn are the sides of a slinky? If I wanted it to make this pattern that I've drawn there, I would have to move the slinky like this. I would grab this end here, this bit here, and I would push it left and right. And the wave actually travels left and right as well. Okay, there are lots of videos on YouTube, or if you have a slinky, please have a go. So for longitudinal waves, the oscillation is parallel to or in the same direction as the direction of travel. Okay. Now, something very important about waves to note is that they transfer energy, but they do not transfer matter. So matter is anything, almost anything really, anything that has a mass, any kind of stuff, that's all matter. So if you imagine an ocean in the wave, okay, this is not the best wave, and this is my boy, as in B-U-O-Y, not B-A-Y. You might have seen, or even with boats as well, you might have seen in the ocean that they will bob up and down on the waves, but they don't actually move from position X to position Y, for example. And that is because waves do not transfer matter. Okay? Again, there'll be lots of videos that you can have a look at of things in the ocean or on any type of wave where they are not moving their location. Okay, so examples of both. For longitudinal, the main example is sound. So sound waves. So you're hearing me right now because the air particles near my mouth. I'm producing an oscillation. The particles here, maybe you can see that arrow just above the wave, are pushing against the particles here and here, and so on, and it will cause this type of wave until it reaches your ear, and then your ear kind of does a lot of jobs too, but we're not going to talk about that. The most obvious example of transverse waves are Sometimes my computer, if I do anything too curly, it thinks I'm trying to produce a circle. Electromagnetic spectrum. So anything in the electromagnetic spectrum will be a transverse wave. So that could be radio waves, gamma rays, any of that. Okay. So speaking of the electromagnetic spectrum, I'll do a separate video for that. But things to note is that all of the waves in the electromagnetic spectrum will travel at the same speed. So even though we say the speed of light, we could just as easily say speed of infrared or speed of ultraviolet, speed of radio waves, speed of microwaves, etc., etc. I suppose we picked light probably because it's the one that we can see with our eyes. So, but I don't know for sure. So what else do I need to say? So we've talked about the two types of wave. We will need to talk about a few equations and labeling the parts in the wave. So I think that's what I will do next. Let's label the parts on the wave, and we'll talk about sound waves as well. So I might zoom in actually. I don't know why I chose blue, but I have. Okay, first thing, where should we start? Let's start with this blue line here. We call this our equilibrium position. Okay, then we will talk about, what do we call the top of the wave? We call that, it has two names, the peak or the crest, and I tend to call it the peak, but it doesn't really matter. The bottom of your wave is called your trough. When I say bottom, I mean the very bottom. And your amplitude, put A here, can either be the distance from the equilibrium position to the peak or the distance from the equilibrium position to the trough. It doesn't matter. And amplitude is a special type of displacement. So your displacement is anywhere between the equilibrium position and the wave. So that's, I'm going to make it a bit less thick. So all of these in pink are displacements. It just happens to be that the amplitude is the maximum displacement. Okay, the wavelength, I will do that in green, is essentially the distance between a point on a wave and a corresponding point on the next wave. And I've drawn that with lambda, which is a Greek letter that basically means wavelength, and that's measured in meters. But you could also do that in other places. I tend to pick the peaks just because it's really obvious where the same point on the next wave is. Another obvious one is trough to trough. You can do it anywhere, however, it just is more obvious when you talk about the peaks or the trough. So for example, I could do it from this point here, but then I need to go to here's the next one, and it's just ever so slightly more difficult to tell where the next point is. And if I did it here, for example, I could do it anywhere, but peaks and troughs are the most obvious. What else is there? Right, the frequency. So the frequency is essentially how many complete waves pass a point in 1 second or per second. Okay, so I tend to think of a complete wave, and this is not an official definition, so don't write this anywhere, as it going down once and up once, all the other way around. So it can go up once and down once. That's one complete wave. So how many of those pass a point per second is your frequency? So per second is the same as writing this, s to the -1. However, that's not technically what we write. We tend to write hertz instead. Sorry, I need to mute that. So per second is also written as h, z, capital H, lowercase z. That's not 2, and that means hertz. So we always say hertz, but just to give you some understanding, that means per second. So 50 hertz means 50 per second. So 50 waves per second. Okay. Now just notice that there is a relationship between the wavelength of a wave and the frequency of it, because if we compare these two waves I'm about to draw, you can see in A the wavelength is a lot smaller, so from here to here is a lot smaller than in B, from here to here. But that also means if the wavelength is shorter, if the wavelength is less, then the frequency will be more, because more waves will pass a point per second. Whereas in the bottom one, if your wavelength is bigger, then your frequency is smaller. Okay? And let's then have a look at sound in particular. So I'm going to draw a few examples. Again, A. I'm not going to do it with a ruler just because I'm lazy. But if we imagine, okay, this is A, so on. B. Again, let's draw my equilibrium position. C. Oh, stop moving. C is going to be C. D. Okay, so for sound waves, you're normally looking for two things to determine properties of that sound, and those are the amplitude and the frequency. So we will compare B, C and D to wave A. I'm going to pick another colour just because I'm a bit bored of using the same colour. So B compared to A, you will notice that it has the same amplitude. So that is the same as that. But the wavelength is longer in B, therefore the frequency is smaller. So in B, the frequency is smaller or lower. Therefore, that's what these three dots mean. Therefore, the sound, because we're talking about sound waves here, is is deeper, lower pitch. Okay. So that is the effect that changing the frequency has. That's probably not that new of an idea to you. So the frequency determines the pitch, whether it's high or low. So let's look at C, starting right in C. So the difference between C and A, you can see that the wavelength is the same. So distance from one peak to the next peak is the same in A as it is in C. However, the amplitude has doubled. It's gone from 1 square to 2. Therefore, in C, the amplitude has doubled. Therefore, the sound is twice as loud as in A. Cool. Right, let's look at D. That's right in here. In D, let's have a look. So D is basically combining both B and C. So it has double the amplitude and double the wavelength, therefore half the frequency. So in D, the amplitude has doubled and the frequency has halved. Therefore, it is twice as loud and as deep than in A. Okay, so that just gives you an idea of the effect that changing properties of the wave has if you're dealing with sound. And the final thing we'll talk about in this video, I think, is going to be the equations we need to know. So I'm going to change to blue now. First one I'm going to write is T equals 1 over F. So there we go. So T stands for time period. I will tend to call it the period, and I think most people would rather than time period. The only reason I said time period is to kind of give you an indication of why I've used, or not why I have used, but why we use T. Okay, so time period is 1 over the frequency, and therefore, if you rearrange that, that also gives you frequency is 1 over the period as well. Okay, and the one that I think is just really crucial is, actually I'll write it here, it's called the wave equation. And that is V equals lambda F, or wave speed equals wavelength multiplied by the frequency. Very important equation in terms of the wave section. Okay, and if you're somebody who likes to use the triangle, not most physics teachers aren't a fan, but I'm not too bothered really. If it helps you to rearrange, it helps you to rearrange. V lambda F, and therefore rearranging that equation gives me two other equations, well, sort of the same equation but rearranged. Wavelength equals wave speed over frequency, and frequency equals wave speed over wavelength. Just remember that wave speed is measured in meters per second, also written like this, ms to the -1. If I think of anything else, I'll probably do another video. I'll do a video for electromagnetic spectrum in particular as well. Okay, bye bye.